In this tutorial, we will see how to use a heuristic to try and minimize either transportation cost or transportation distance within a plant. In these types of problems, it is not necessarily the case that the distance required to move work from Department A to Department B is the same as the distance required to move work from Department B to Department A. Why? The biggest reason is one-way routes within the plant. Nevertheless, we will assume that the distance between any two locations is the same regardless of direction. Additionally, it is not necessarily the case that the distance required to move work from Department A to Department B and then to Department C is necessarily the same as to move work directly from Department A to Department C. Why? The biggest reason may be that work not coming into a department is not allowed to move through that department. Unlike equal directionality, we will not assume that distances between departments can be added. We will assume that costs are a direct function of distance. That is, if you double the distance, you double the cost. That means that minimizing distance also minimizes cost. This most likely is not the case, but making this assumption greatly reduces the complexity of these types of problems. Just for information, why might cost not be linear? Consider moving something by forklift. Part of the cost is simply getting the forklift to the department. That cost is the same regardless of how far the work is to be moved. As the distance the work is to be moved increases, the fixed cost of bringing in the forklift is spread out over more units of movement. This spreading out of the fixed cost over more move units decreases the cost per move unit. However, as I said, we will ignore this. Finally, just to repeat, this process is a heuristic. That means it finds a good solution, but not necessarily the best solution. Finding the one best solution requires more advanced mathematics. As a heuristic, not everyone working a problem will get exactly the same answer. The more involved the problem, the more likely this is to be the case. This plant has three locations, A, B, and C. Moving from A to B is 15 meters. Moving from B to C is 40 meters. Finally, moving from A to C is 60 meters. The center is grayed out because it does not make sense to talk about the distance from A to A, B to B, or C to C. The area below that is yellowed out because we are assuming the distance from A to B is the same as B to A, so the yellow area is redundant. The plant has three work centers, 1, 2, and 3. There are 50 moves from Work Center 1 to Work Center 2. There are 200 moves from 1 to 3. Finally, there are 120 moves from 2 to 3. We wish to assign departments to locations to minimize movement. The screen shows most of example number 1 visually. You can see the three locations, with Work Center 1 arbitrarily assigned to A, 2 assigned to B, and 3 assigned to C. The lines show the distance and why A to C is not A to B plus B to C. What is missing from the diagram is the number of moves between the departments. The most moves are the 200 between 1 and 3. The shortest distance is between A and B, so we know we wish to assign 1 to either A or B and 3 to the other. What we do not know right now is which gets A and which gets B. The second highest number of moves is between 2 and 3. Thus, it is more important to have 2 near 3 than 1. That results in the layout of assigning 1 to A, 3 to B, and 2 to C. Now that we have the arrangement, we can figure the total meters moved. For each pair of locations and matching work center assignments, we multiply the distance times the number of items moved. For A to B, we have assigned 1 and 3. For that combination, 15 times 200 equals 3,000. For B to C, 3 and 2 are assigned, and 40 times 120 equals 4,800. Finally, A to C has 1 and 2 assigned, and 60 times 50 equals 3,000. Those total to 10,800. 10,800 is neither good nor bad, as we have nothing to compare it to. If you tried another arrangement, you would compute the same number. If it were higher, then the new arrangement is not as good. Also, if you had the cost per meter, this number would allow you to compute the cost of movement. Here's an example for you to try. A plant has the distances between locations and movement between work centers shown on the screen. Assign the work centers to locations to minimize the amount of movement.
Since you've seen an example already, let me suggest that you pause the video and try to work this problem on your own. Once you're done, you can use the video to check your work and spot any mistakes you might have made.
The longest move is A to D, and the least amount of work flows between work centers 3 and 4, so it makes sense to assign 3 to either A or D and 4 to the other. The most amount of work flows between 1 and 2, dwarfing all the other moves. Locations B and C are the closest, so it makes sense to assign 1 to either A or B and 2 to the other. All of the other pairs of distances are either 50 or 60, so they are roughly the same. All of the other movement levels are between 30 and 40, so they too are roughly the same. Thus, they do not really help us decide on the arrangement. Without any compelling reason to go one way or the other, we arbitrarily assign 3 to A and 4 to D. Likewise, we arbitrarily assign 1 to B and 2 to C. In all likelihood, switching these two pairs of assignments would result in roughly the same cost. Interested viewers should check that assumption to be sure. The screen shows the solution visually, although distances are shown but not the number of moves. The screen shows the cost calculations. The total meters moved is 14,900. If you decide to rework the problem and swap out the AD and BC pairs, this is the number you would use for comparison. If this video helped you working operations management problems, please consider liking the video and subscribing to the channel.